All right, now we get to talk about differential equations that we haven't learned how to solve yet. So we don't have a method for how to solve these yet. So say we need to solve a differential equation. We can't do it with the following methods like we've done in the past, memorizing like arctangent, power rule, or u substitution. Also, the equation involves both x and y, so the fundamental theorem of calculus doesn't really work out. So now what do we do? Okay, so there are actually a lot of different ways to solve differential equations. We're going to learn one called separation of variables. So, a differential equation in this form, dy dx equals a function of y times a function of x, is called separable. It's key that these are being multiplied together. So, what we're going to do is separate the variables by writing the original equation in this form. 1 over the function of y equals the function of x times dx. So we're going to get all of the functions of y on one side, all of the functions of x on the other side, separating the variables. And the solution is found by anti-differentiating, integrating each side with respect to its isolated variable. So we're going to integrate this side with respect to dy, and this side with respect to dx. We can treat dy and dx as simple variables, meaning we can break them apart. If you want to see proof of this, go ahead and Google Leibniz shortcuts for anti-differentiation if you're interested. So, first example. Solve the following for y, given that y equals 2 when x equals 0. So that's our initial condition. That's how we're going to solve for c. Given this differential equation, dy dx equals negative x over y. So we need to get all of the y's on one side and all of the x's on the other side. So what we're going to do is multiply both sides by y and multiply both sides by dx to get y dy equals negative x dx. So do you see how I multiplied both sides by y to get all of the y's on the left-hand side, and then I multiplied both sides by dx to get all of the x terms on the right-hand side. Now we're going to integrate both sides, and on the left-hand side we get 1/2 y squared plus c. And on the right-hand side we get negative 1/2 x squared plus c. So you might say, well, why do we have two c's here? So for this kind of equation, for separation of variables, we can actually just combine this as one c, because a constant is a constant plus a constant is a constant minus a constant is a constant. So we can write this as 1/2 y squared equals negative 1/2 x squared plus c. So we can just combine these two c's. Now our initial condition. So our initial condition is this. So we're going to solve for c. So y is 2 when x is 0. So I'm going to go ahead and plug in 2 for y. So we get 1/2 2 squared equals negative 1/2 when y is 2, x is 0. So equals negative 1/2 0 squared plus c. So this term here becomes 0. And now we got 2 squared, which is 4, times 1/2, which is 2. So we get 2 equals c. So we got 1/2 y squared equals negative 1/2 x squared plus 2. Alright, now there are two different kinds of solutions you can have, an implicit solution and an explicit solution. And that just means, did you solve for y or not? So this right here is an implicit solution because we didn't solve for y. Okay, so now I'll solve for y, and that'll be the explicit solution. So our question said solve the following for y, so they're looking for an explicit solution. So first we'll multiply both sides by 2, so we get y squared equals negative x squared plus 4. And then we'll take the square root of both sides, so we get y equals the square root of negative x squared plus 4. Or 4 minus x squared. And this is the explicit solution. All right. And that is one example of how to use separation of variables to solve a differential equation. Now let's look at another example. All right, solve for y if dy dx equals x times y squared and y equals 1 when x equals 1. So this is dy over dx equals, I'm going to write this as x squared times y squared. So then we have two separate functions, clearly. Now we're going to put all of the y's on the left-hand side. So this is going to be 1 over y squared dy, and multiplied by dx equals x squared dx. And I'm going to rewrite this so that we can integrate it easier. Y to the negative 2 is the same as 1 over y squared. dy equals x squared dx. Now we integrate both sides after we separated the variables. And for this one, for the left-hand side, we add 1 to the exponent, so this is going to become negative y to the negative 1 plus c equals 1/3 x cubed plus c. All right, so we can simplify this a little bit to become 1 over y, negative 1 over y equals, we'll combine the c's just like we did in the last problem, 1/3 x cubed plus c. Now we'll use our initial condition. So when y equals 1, so we're going to go ahead and plug in 1 for y. And when x equals 1 as well, so we're going to go ahead and plug in 1 for x to find c. So negative 1 over 1 is negative 1. 1 cubed is 1 times 1/3 is 1/3 plus c. So that means we subtract 1/3 from both sides and we get negative 4/3 equals c. Now, our solution, almost. So, plugging in c, kind of draw an arrow from here too. So we're going to end up with negative 1 over y equals 1/3 x cubed minus 4/3. So now, if we want to solve for y, we need to, let's first write this as a different, let's combine the fractions on the right-hand side. So this is negative 1 over y equals, do you see how these are both fractions over 3? So we're going to write this as x cubed minus 4 all over 3. Okay, now we're going to take the reciprocal of both sides. So to make this negative y equals 3 over x cubed minus 4. And then to solve for y, we'll multiply by negative 1. So y equals negative 3 over x cubed minus 4. And that is the explicit solution to this differential equation up here. Now we'll take a look at one last problem, which is kind of an introduction to population problems that we're going to look at next in the next video. So we got this differential equation dp over dt minus 2p, and this initial condition, p of 0 equals 1. Let's find the solution to this differential equation. So our two variables now are not x and y, but they are p and t. So we need to get all of the p's on one side and all of the... Oh, Excuse me. How about an equal sign? That will help. Now it's an equation. Okay, all the p's on one side and all the t's on the other side. So we're going to put all the p's on the left-hand side. So we're going to divide by a p. So this is going to be 1 over p dp equals multiplied by dt, negative 2 dt. Now we're going to integrate both sides. Remember that the integral of 1 over p is the natural log of the absolute value of p equals, let's see, this is going to be negative 2t plus c. I'm just combining the c's on one side in one step this time. Now our initial condition. That's what that IC is. All right, p of 0 equals 1. Which means if we plug in 1 for p and 0 for t, we can find c. So this will become the natural log of the absolute value of 1 equals negative 2 times 0 plus c. So natural log of 1 is 0. Negative 2 times 0 is 0, so 0 equals c. Which means that the natural log of p, the absolute value of p, equals negative 2t. Now, this would be an implicit solution, but we'll go ahead and find the explicit solution. So, to counter this natural log of p, we're going to take the exponential of at both sides. So the exponential of the natural log of absolute value of p equals e to the negative 2t. Because now on this side, e to the natural log of something is that something. So now the absolute value of p equals e to the negative 2t. And now you can double check me on this, but e to the negative 2t will never be 0. So since e to the negative 2t will never be 0, we actually don't need this absolute value because this term on the right-hand side will always be positive. So we can just write this as p equals e to the negative 2t. And this is important. We'll talk about this solution in the next video. There's something special about this population equals e to the something. Okay, so that is separation of variables. Please email me if you have any questions at all about this.